Welcome everyone, my name is Machaček and today I will introduce to you the software Numgeo and its integration into the pre- and post-processing tool GiD. Numgeo is a finite element code mainly focusing on geotechnical engineering. As of today, we are a team of 8 developers from different universities in Germany contributing to the various parts of the code. Numgeo also features a very rich HTML documentation, giving access to detailed installation instructions and tutorials, as well as showcasing the accuracy of the implementation by means of benchmark simulations. The main features of Numgeo are various finite element formulations, different hydraulic and mechanical constitutive models, as well as robust advanced contact algorithms. As Numgeo focuses on geotechnical engineering, we implemented various multi-phase finite element formulations, allowing to describe dry soils, saturated soils, and partially saturated soils in the framework of the theory of porous media, not only in static and transient conditions, but also in the transient dynamic conditions, including the effect of inertia. For modeling the stress strain behavior of different soils, we give access to basic constitutive models such as the Numgeo model or modified clay model, but also to more advanced constitutive models for sand like the hypoplastic model with intergranular strain extension or the semi-sand model family, as well as for clays, for example with the Avisa model incorporating viscous effects. Those models are very well suited for modeling the behavior of soils under monotonic and cyclic loading. For high cyclic loading, we implemented special high cycle accumulation models for sand as well as for clay. For the hydraulic models, we implemented different soil water retention curves, starting from very basic models like the Brooks and Corey or Fretland and Xing model to a more advanced constitutive model like the Karlsruhe model or the Gao model, incorporating effects of void ratio and also being capable of modeling hysteresis effects during cyclic drainage and wetting. In addition, we feature several models for the relative permeability, also different approaches to incorporate the suction into the effective stress, as well as different models for the permeability. For interface modeling, we rely on mortar methods. Mortar methods are very suitable to model large relative displacements in the interface and are known to have a reduced mesh dependency. For the frictional behavior, we implemented basic contact models such as the Coulomb friction model, but also more advanced constitutive models like the semi-sand constitutive model or a hypoplastic model with intergranular strain extension. If the inbuilt features of Numgeo are not suitable, users can easily extend the capabilities with their own codes using so-called user subroutines. This could, for example, be user boundary conditions, user initial states like the user initial stress or void ratio, but also user-defined materials for saturated and dry soils, but also for unsaturated soils. To demonstrate some of the capabilities of the software, we present 2 examples. The first example deals with the deep vibratory compaction. During deep vibratory compaction, a vibrator is inserted into the soil. The vibrator is then turned on and slowly in a stepwise manner pulled up the ground surface. Due to the vibration, the soil is compacted in the near field of the vibrator. Modeling such a process is very challenging since the soil is subjected to several thousands of loading cycles. The approach that we followed is based on the HCA model, so the high cycle accumulation model. A representative simulation result is shown here on this slide. On the right hand side of the slide, you see the evolution of the void ratio during pull-out of the vibrator. The dark blue areas show a decrease of the void ratio and thus a compaction. The second example deals with the back calculation of a centrifuge test on shallow foundations under earthquake loading. The experiments have been performed by Seibek and Manabushi. The finite element model of the centrifuge test is displayed on the right-hand side of the slide. Also visible are the 2 locations where pore water pressure was recorded, P6 and P10. The recorded pore water pressures from the experiment in black and from the simulation in color are shown on the right-hand side of the slide. We can see that the simulation results match very well the experimental data for both the UP formulation and the UU formulation. Performing a finite element simulation with the code Numgeo includes the 3 stages that are very common in finite element modeling. The first stage is the pre-processing, then the calculation, and then the post-processing. During the preprocessing, the finite element model is created, including creation of nodes, finite elements, defining material properties, and assigning boundary conditions and initial conditions. This is done in Numgeo using a text file approach. This text file is then read by Numgeo and processed. The results of this calculation can then be seen using ParaView or in a standard text file. Obviously, the preprocessing stage is not very user-friendly and might be quite error-prone. For that, we decided to leverage the preprocessing capabilities of GiD. It offers quite powerful CAD and meshing features and also allows us as developers to create a guide for the model creation. GiD allows us to easily design an intuitive data tree that gives a seamless guide to users through the creation of the finite element models. With the assistant generation of material definitions and initial conditions and loading sequences, which only show the relevant settings to streamline the user experience. This is demonstrated here on this slide by example of the material definition. The first material on the left-hand side, the material for dry soil, having only the grains as one phase. For such material, the density has to be given and a stress-strain model needs to be specified. In this case, we chose the hyperplastic model with intergranular strain. If we increase the complexity and we consider a saturated soil, we have to consider the pore water in addition to the solid. So we have two phases. But this also requires the definition of a permeability, or the bulk modulus of fluid phases, or a dynamic viscosity of the fluid phases. If we increase complexity even further and we consider a partially saturated soil, we have to consider the pore air in addition to the pore water and the solid grains. Thus, we consider three independent phases. This, however, again requires a definition of more constitutive models, like the soil water retention curve or the relative permeability model. GiD also allows for a very intuitive assignment of materials, initial conditions or boundary conditions to different components of the finite element model. This is displayed on the right-hand side for the example of a retaining wall. By defining default values for various advanced settings like the linear equation solver or convergence criteria, GiD allows us to give transparent access to these advanced settings. At the current stage, Numgeo only integrates into the pre-processing capabilities of GiD. Current work focuses on integrating Numgeo seamlessly into the GiD pre- and post-processing capabilities, allowing not only for the pre-processing, so the model creation, but also to start and monitor a simulation from within GiD and also perform the post-processing in GiD. With that, I'm at the end of this very short introduction. I thank you for your kind attention, and if you are interested in downloading Numgeo or want to read more about it, you can use one of the QR codes displayed below. Thank you.